Hello there, and welcome back. In this video, we're going to be introducing you to a software that can be easily accessible online for free, and this software platform is called Desmos. You can find it at www.desmos.com/calculator, and then you can start doing some of the things that I'm about to show you that it can do. So one of the very basic things that Desmos is useful for is dealing with functions, calculus, representations of graphs. There are, of course, some other applications such as GeoGebra that does have their strengths, but I personally find Desmos very easy to use, especially for some of the basic things that we usually do, for example, in statistics, calculus, or pre-calculus. So let's just start off by just a couple things. So let's assume we want to define a function and want to evaluate that function at a particular point. So I can start typing f of x is equal to whatever function you have. So let's assume I want the function 5x squared minus 2x plus 1, which is of course the graph of a parabola. So over here you can see that it does graph this perfectly well. If you don't like these graphs, you can always go up here to the little toolbar and you can change your graph settings, for example, the grid on and off, the x-axis scaling, the y-axis scaling, and several other things you can use. Or you can change the color or the thickness of this graph by going up to this little tool widget, and then you can click this blue dot, and there's a bunch of settings that you can definitely play around with here, just in case you were feeling curious. So that is the graph of my parabola, 5x squared minus 2x plus 1. If I want to evaluate that function at a particular point, I can just do f of negative 3 on another line, and that will give me 52. That means if I were to plug in negative 3 into this function, I would get 52 as my particular output. Now, what if I want to deal with, for example, piecewise functions? Desmos can do piecewise functions very well. So let's assume I want to define a piecewise function g of x that has 3 different pieces. So if it's multi-pieces, then you have to start with a little brace. So let's assume the first piece I want to define is negative x squared plus 3x plus 1. And let's assume that I want that curve to be defined on all real numbers less than 1. So I need to precede that function with x less than 1, and then separate the domain definition with the function, and that will give you the graph of that little piece, which is very, very nice. So what if I want to add another piece? So what I can do is I can do comma, then the next domain of definition, so negative 1 less than or equal to. So once I press this equal to sign, they will combine into 1. And that's going to give us x is less than or equal to 2. So let's assume that's our next piece of the function. And let's assume we want to define that to be, say, the line 3x minus 2. So that gives us our next piece. And then the next piece, let's assume we want to be a periodic function on the interval x is greater than or equal to 2. Let's define it to be equal to the sine function sine of x. Right? So that gives us a piecewise function here. If I were to evaluate this function anywhere, it should give us values on those particular pieces. So 0 will be associated to this parabola. 1.5 will be associated to this line, and anything after 2 will be associated to that sine curve. So you should get a number between negative 1 and 1, regardless of what number you put here, because that's the range of my sine function, right? So those are just some of the basics associated to graphing functions, piecewise functions, and so on. So what else can Desmos do that might come in handy? Solving equations is a very common problem that you can see across a variety of different fields. So let's assume we want to solve the equation 8x squared minus 2x minus 3 is equal to 0. So one thing I can do is I can begin by defining a function. Let's call this function h. Right? And let's define it to be that function that's set equal to 0. So 8x squared minus 2x minus 3. And let's turn off this other function since we're focusing on that. So the points for which this curve is equal to 0 is precisely the x-intercepts. So if you hover above these particular numbers, then that will give you an approximation to the solution. But sometimes the solution might not be so obvious. For example, let's do, instead of ax squared, let's do something fancy, like 4 times sine of x times cosine of 3x or something like that. So let's assume I want a particular solution on this region. Let's assume I want this solution here that's hanging out in between 0.5 and 1. So let's just do a domain restriction, so 0.5 less than x less than 1. So I'm only interested in this particular solution. I mean, of course I can click that, but what if I click it and I don't get, the amount of decimal precisions that I want for that particular number? So if I want that particular x value, what I can do is I can use 0 tilde h of the name of that point. So let's assume I want to name that point A, and that's going to give me an approximation for that particular value that I want. So in this particular case, I have that the x-intercept is approximately equal to 0.523598, which is precisely equal to pi, which is pi, divided by 6, which is, of course, the same exact thing that it shows here. Right? So solving equations, easily done in Desmos. That's not that big of an issue. What about if you're in, say, calculus? What about derivatives? Can it do derivatives very easily? The answer is, of course, yes. Let's define a new function. Let's call it j of x, and let's assume this function is equal to sine of x plus 0.32x plus e to the power of negative x. So we have a new function here. And let's assume we want to find the derivative of this curve at x is equal to 2, right? So when x is equal to 2, we clearly see that this curve should be decreasing, so the derivative at this point should be negative. What I can do is I can do j prime of 2, and that will give me the derivative of j when x is equal to 2. What if I want to graph the line that is tangent to this curve at this particular point, or the linear approximation? So in case you learned this in calculus, the linear approximation to this curve is going to be equal to the derivative at that point times x minus that value plus the vertical height of that value. So this is the linear approximation to this curve at this particular point. So what are we using linear approximations for? So we have this very complicated function possibly. So if we plug in like 2.3 into this function, maybe we don't know what that is, but these are all pretty numbers, right? Number times x minus 2 plus number, that's a very easy thing to do by hand. So I can get my linear approximation to this function at 2.01, and I get, approximately 1.68, which should be close to the original, right? That's the point of linear approximations. So that is how you can do derivatives and tangent lines and linear approximations in Desmos. Also not that difficult of a thing. What about integrals? Integrals are pretty exciting things. So let's just delete these curves. So notice I'm not deleting them, I'm just sort of hiding them. Now keep in mind, you cannot define L of x again, because then it probably, or should actually, start fighting each other, because these are the same name for the different things. Usually, especially if you start redefining like f of x is equal to 2x, and then f of x is equal to 3x. Technically, if I do like f of 3, it doesn't really know what to do with that, because it's like, if you define f in more than one place, technically these should not be graphing. So make sure you're not redefining the function, else you're going to come across a lot of issues there, right? So let's just assume everything has different letters. So what about the areas under curves, right? So integrals. So in order to calculate an integral in Desmos, what we can do is do int of something, right? So let's define a function. Let's call it capital N for Nemo. So capital N is going to be equal to, so let's do a fraction, e to the minus 0.3 x all over x. And let's multiply that by, let's say, sine of 20x plus 2, right? So it's a wavy decreasing function as x goes to infinity, right? So as this goes to infinity, this appears to go to 0 or something close to it, right? So let's assume I want to find the area under this curve on a particular interval. So I'm just going to shade it here. Let's assume I want to shade the values, all the y values, less than or equal to this function, but on a particular region. Let's assume 1 is less than x less than 2. So notice this region here isn't a pretty shape. It's not the shape of a rectangle or a triangle or a circle or something. It's just some region. So as you already know, integrals can calculate the area of that with no particular issue. So to do an integral in Desmos, you're just going to type in I, N, and once you press T, the integral should pop up. So we want to integrate the function 1 to n, and which function do we want to integrate? We want to integrate n of x dx, and this is going to be the area that is shaded here in this picture in green. So integrals also not that bad, and you can also do indefinite integrals with infinity and minus infinity, also with not that big of an issue. So that's how you can do integrals in Desmos, also not so bad. So what about improper integrals? So let us define the gamma function. A gamma function is an analytical extension of the factorial function, because you know that the factorial function is only defined on the natural numbers. 0 factorial, 1 factorial, 2 factorial, 3 factorial. It's just the product of all of its preceding natural numbers. So one of the smooth curves that sort of pass through all those values is what we call the gamma function. And the gamma function, which I'm going to call capital G, is defined to be equal to the integral from 0 to infinity. So to type in infinity, it's INFT, and then once you press Y, it's going to give you infinity. And we're going to be integrating the function t to the power of x minus 1 times e to the power of minus t dt. And this generates the graph of the gamma function, right? So this is our gamma function. So of course it's increasing, as we know factorials typically do. So 0 factorial is the same as gamma 1. 1 factorial is the same as gamma 2. So you can clearly see that gamma of 1, that's 0 factorial. Gamma of 2, that's 1 factorial. Gamma of 3, that's 2 factorial. Gamma of 4, that's 4 factorial. And of course the list goes on. But the useful thing about a gamma function is to figure out, what's going on in between these factorial numbers. So let's assume we want to evaluate gamma at, say, 1.5. So gamma 1.5 is going to be approximately equal to 0.88623. Now, one can ask, well, is there a pretty value for the gamma function at 1.5? The answer is, of course, yes. But that's more for a theoretical calculus course. But you should be able to prove, if you have some calculus background, and that's actually just going to be equal to the square root, so sqrt of pi all divided by 2. So proving that gamma of 3 halves is the square root of pi over 2, that's a theoretical exercise for you fun calculus people. But from a practical perspective, as long as you can evaluate gamma at any values to some degree of accuracy, and then use that to, say, solve probability problems, usually that's all you need to do. So that's just a brief introduction to Desmos and some of the things it can do. For example, plotting functions, evaluating functions, piecewises, derivatives, tangent lines, integrals, integral defined functions, and there are several other things. For example, painting pictures using functions and parametric curves and so on. But anyway, this is just an introduction. If you're interested in those things, I definitely can make a follow-up video to this. But until then, I will see you later. Take care.